Now that you have an understanding of correlation, it's time to dive into regression analysis, which is closely related to correlation but a little bit more complex. We will go over the basic concepts without getting too much into the technical details, but as we have done in the past, we will show you how to run a regression and how to interpret the results. Let's start by looking at the same tape data as before and the scatter plot you already saw between price and units sold. It's best if you follow along with the Excel file open on your computer so you can learn how to do this. Select the scatter plot, click on the plus sign and check the box for trend line. Then right-click on the trend line and select Format Trend Line. In the dialog box, check the boxes for Display Equation on Chart and Display R-squared value on chart. You should now be able to see the regression equation and the R-squared value on the chart. Look at the regression equation, but more importantly, look at the R-square. As we will see, R-square is a number from 0 to 1 representing the percent of variance in the dependent variable, sales, that is explained by the independent variable, price. For this regression, the R-square is 0.004 or less than 1%. So this confirms our earlier finding that the variables are not correlated. In general, the objective of regression is to quantify the relationship between a dependent variable y, also known as a criterion variable, and one or more independent or predictor variables x. We use regression both to understand the effects of the x's and to predict or forecast the value of y for the given values of the x's. It's a widely used technique employed in almost every field, from marketing, where it is used to predict sales as a function of marketing mix variables, to economics, where it is used to predict the gross national product based on macroeconomic variables such as money supply. The basic or simple regression model assumes that y equals an intercept term, beta naught, plus a regression coefficient, beta 1 times x, plus an error term, epsilon, that captures the impact of any other factors that affect y but are not observed. The intercept term represents the mean value of y when x equals 0. The slope or coefficient of x represents the change in the mean of y due to a 1-unit change in x. A simple regression model has just one x, and when you have more than one x, it is called multiple regression. Without going into the math, let's take a look at the logic of how the regression line is fitted to the data. The basic idea is that we want to find the line that best predicts the value of y, that is, has the least error between the data points and the line. Since we are not concerned with whether the error is positive or negative, that is, whether the data point lies above or below the line, since both are equally bad, we square the error so that negative or positive errors don't matter. For example, errors of -5 and +5 when squared both equal 25. Consider the dotted blue regression line in the figure. The error for each data point is defined as the difference between the point and the line. Some points shown in red have been highlighted to show that the error means the difference between those points and the line. So we square that error for each data point in the plot, add up all the squared errors, and that is the total squared error for that line. We do this for all possible regression lines, and the line with the lowest error is the best fitting line. Now we've been talking about R-squared, and earlier we were talking about the correlation coefficient R, so we need to understand the difference between them. The correlation coefficient, lowercase r, has values between -1 and +1. It measures the strength and direction of the linear relationship between two and only two variables. To determine if the correlation between the variables is 0, we can conduct a statistical test. R-squared, also known as the coefficient of determination, is found in regression. Its values lie between 0 and 1. It's a measure of how well the regression line fits the data and what percent of the variance in y can be explained by the x's. Importantly, it can be used when there is more than one x. We can also conduct a statistical test to determine if the R-squared is significant, that is not equal to 0, which would mean that the x's explain some of the variance in y. So let's take a crack at running our first regression using the tape data. You will need to use the data analysis add-in in Excel. If you don't have it, check out the link to the video that shows you how to install it. Open the file, and once you have the data analysis add-in running, select regression in the list of options. We will include both price and ads as our independent variables. Enter the input ranges for y and x and the output range as shown. Check the labels box and click OK. Here's what the output will look like. There are 3 sections. The first called Regression Statistics, the second called ANOVA for Analysis of Variance, and the third showing the regression coefficients and the intercept. That's a lot of numbers to digest, but luckily you can ignore most of them. Here are the 3 most important things for you to look at in the regression output. First, the goodness of fit of the model, or the percent of variance explained, as shown by the R-square. In this example, it is 0.47987, meaning about 48% of the variance is explained. A higher number is better because it means the regression fits the data better. A quick note about the adjusted R-square, which is also shown here. It is used when comparing different regressions that have a different number of x's. In other words, it is adjusted for the number of x's in the regression. No need to worry about it here. Second, in the section called ANOVA, look at the last column, at the value under significance f. This shows the p-value for the test for the R-squared. In this example, the p-value is less than 0.05, which is our cutoff for alpha, which means that the R-squared is significantly different from 0, and the x's do explain some of the variance in y. Third, in the last section, look at the column titled p-value. This shows the p-values for the tests for the coefficients. In this example, the p-value for add is less than 0.05, but for price, it is greater than 0.05. So we conclude that the coefficient for price is 0, but for the add, it is significantly different from 0. Here, the coefficient for add is 1266.84, which means that every time an add is run, sales increase by that many units on average. Since only add was significant in the last regression, we can remove price from the regression model and estimate a regression with just add as the independent variable. Now, looking at the output, we see that removing price did not make much of a difference. The R-squared is still 48%. The test for the R-squared is still significant with a p-value less than 0.05. The coefficient for add is also significant with a p-value less than 0.05. The last thing you should note is the number for residual MS, which means mean squared error. We will come back to it shortly. Here's an assignment that will give you some practice on running a regression. You'll find the assignment and the data on Blackboard. And now we come to the final step, using regression for prediction. How do we make a forecast? Well, we start with the last regression model we estimated with add as the only independent variable since price was not significant. The model that we estimated was y equals 1195.18 plus 1266.01 x, where the first term is the intercept and the second term shows the coefficient of add. We can predict sales for 2 values of add. First, when add equals 1, and the second, when add equals 0. The first refers to the case when the add is shown, and the second when it is not. When add equals 1, predicted sales equals the intercept term plus the add coefficient times 1 for a total of 2461.19 units sold. When add equals 0, the add coefficient is multiplied by 0, so predicted sales are equal to just the intercept, a value of 1195.18. Now these are called point estimates because they provide a single value for the forecast. But because the regression line does not fit the data perfectly, remember it only explains 48% of the variation in sales, sales may be higher or lower than predicted. So we can hedge our bets and get a range of values within which the actual sales will lie 95% of the time. This range of values is calculated as the point estimate value plus or minus 2 times the square root of the mean squared error. Remember the mean squared error that we looked at a minute ago? In this example, the mean squared error is 311962.8. So 2 times the square root of this is 1117.1. Now we are ready to calculate the 95% range for the forecast as a point estimate of 2461.19 plus and minus this number 1117.1. And so we conclude that when an ad is shown, the most likely value of sales is 2461.19, and 95% of the time the actual sales will lie between 1344.09 and 3578.29. If that seems like a big range, that's because our regression didn't fit the data very well. It only explained 48% of the variance in sales, so the error in prediction is relatively high. Regression assumes that your data are quantitative in nature, but there is one exception. You can include a variable that has values only of 0 or 1. This is called a dummy variable. In this example with the tape data, the variable ad was assigned values of 1 and 0 to indicate the presence or absence of an ad. Assigning a value to a variable is called coding the variable, so a dummy variable is always coded as 1 or 0. What happens when you need to include a categorical variable in your regression that has multiple values? You would need to represent them via a series of dummy variables, each coded 1 or 0. In general, to represent n groups, you need n-1 dummy variables. For example, let's say you want to include consumer type as an independent variable in the model, and there are 4 types of consumers in your sample: brand loyals, variety seekers, impulse buyers, and rational buyers, coded 1 through 4. To include this variable, you would have to create 3 dummy variables, D1, D2, and D3, to represent the 4 types. As you can see in the table, when the consumer is brand loyal, D1 is coded as 1 and everything else is coded as 0. For variety seekers, D2 is coded as 1 and everything else is coded 0, and so on. You could then run a regression with D1, D2, D3 as the independent variables. Once you get the output, and assuming the coefficients are significant, you could predict the dependent variable by plugging in the values for each of the dummy variables for a given consumer type. For brand loyals, the prediction for Y would be the intercept plus the coefficient for D1, since all the other terms would be 0. For variety seekers, the prediction for Y would be the intercept plus the coefficient for D2. For impulse buyers, the prediction for Y would be the intercept plus the coefficient for D3. And for rational buyers, the prediction for Y would be just the intercept, since all the dummy variables would equal 0. In closing, we should be aware of the assumptions underlying regression, because regression may not be appropriate if the assumptions are violated. First, it assumes that the relationship between the variables is linear. If this is incorrect, then regression can give you very misleading results. Second, it assumes that errors, that is, the effects of unobserved factors on Y, are normally distributed with a 0 mean. Third, it assumes that the errors are uncorrelated with each other. That is, errors for each data point are independent of each other. Finally, it assumes that the independent variables, the x's, are independent of each other, that is, uncorrelated. Researchers sometimes feel the need to test whether these assumptions are being violated, and if there is evidence that they are, there are ways to work around these problems. However, because we are not looking at the technical aspects of regression in this class, we will not go into those methods. These are beyond our scope and more appropriate for an advanced course in statistics or econometrics.